All right, today we're going to take a look at section 4.2. It's titled Area. One of the things that we did when we learned derivatives is we talked about like all of this process behind which that there were just these rules and we just apply these rules, right? But we also talked about derivatives in the sense of what do they tell us informationally, right? They give us maximums, minimums, they give us increase and they give us decrease, and they talk about slope, all that kind of stuff, okay? So this section 4.2 combined with 4.3 is sort of that background of what do antiderivatives tell us. I mean, we can have all this sort of fun, you know, like rules and applying rules, and it just feels a little bit like a game or like a puzzle or whatever from 4.1. But if there's not something behind that, this information is actually giving us, it's kind of just that. It's a game, right? It's just a puzzle. And there actually is information behind what that's giving us. So probably at the end of class today, and maybe even not until we get till Friday, is it going to seem like all these sections come together. So just bear with me through this week, and there will be a point where we connect all the dots, okay? So what we're looking at today is a new notation that you may not have seen before. You may have. Probably depends a little bit on what your high school sort of focused on or what curriculum pieces were available there. But you also may not have. So that notation is called sigma notation. So sigma is the big capital like E-looking sort of shape at the beginning, right? Or S, I don't know what you want to call it, but that's called a sigma. It's a Greek letter. So sigma notation is simply a way of saying we're adding a bunch of things together. It's a summation notation. So sigma, summation, they both start with S, yay, right? Help you with a mnemonic little piece there. It's written like this. So when we have that sigma, the bottom part, that little I, tells you where the index starts, and the top number where it has an N tells you where it ends. So if it starts at 1, it ends at 4, it means there's 4 numbers you're adding together. If it starts at 2 and it ends at 7, that means there's 6 numbers you're adding together. Okay, so it doesn't have to start at 1, although most of the time it will, and I'll show you what happens when it doesn't. But it actually tells you really how many terms are getting added. I is called the index of summation. A sub I is simply the ith term. So A sub 1 would be the first term. A sub 7 would be the 7th term. And then the upper and lower bounds on the summation, or what I was referencing, are the number on the bottom, 1, and the number on the top, n in this case. And n is just representing some other whole number. So these are whole numbers too. Maybe I should mention that. Okay. So we're going to do one from scratch, example number 1, and then I'm going to show you some cool summation formulas that you'll have at your disposal for sort of making a shortcut into finding what you might need to want to find for the others that go a little further down the bunny hole. Okay, so am I good to continue, or are we still completely writing? We're good? All right. So write this down. If you didn't have notes printed out, jot that down. So what you see in parentheses is like an equation, right? Well, an expression anyway. It's got a variable in it, just like when we've done functions. And we're trying to evaluate it at a bunch of points. And after we do all these evaluations, we're going to add them together. Okay? So this notation at the beginning says that I want the sum, right? I'm going to add some things together. The number here on bottom tells you that I'm going to start with I equal 1. So this is going to be called A sub 1. And this number at the top tells you that we're going to go all the way out until we get to I equals 6. So we're going to have A1, A2, A3, A4, A5, and A6. And when we're done, we're going to add everything together. That's what we're going to do. Okay? So the mathematics that we're doing is like middle school stuff, elementary school stuff. We're plugging a number in, we're evaluating, we're adding a bunch of things together. The notation is new. I don't think you've probably seen that notation before, or if you have, it's certainly not been very frequent. Okay, is everybody good so far? So what we're actually going to do is we're going to take this expression and we're going to evaluate it at 1, and evaluate it at 2, and evaluate it at 3. So it's going to look like this: 3 times 1 minus 2, which we'll find in a minute. And I've got 3 times 2 minus 2, and 3 times 3 minus 2, all the way down to 3 times 6. All right, so when we get to a test or a quiz, what do I expect you to show? Do you have to actually show the number like I just wrote? No, you don't. But you do need to show me what you actually get when you plug the number in. So maybe you decide, I'm just going to grab my calculator. I'm going to put in, 3x minus 2 into y1, right? And I'm going to go into the table and I'm putting 1, 2, 3, 4, 5, 6. Fabulous. Go for it. Okay, but you're going to show me the result of all of those. So for instance, 3 times 1 minus 2 is 1. 3 times 2, sorry, hang on. Negative 1. No, 1. I was right the first time. I was moving on too quickly. 3 times 2 minus 2 is 4. 3 times 3 minus 2, 7. 3 times 4 minus 2, 10. Do you notice a pattern with these numbers that I'm getting? Yeah, they're going up by 3 every time. This actually has a name. It's called an arithmetic sequence. Maybe you remember that, maybe not. But anytime something just sequentially adds a number every single time in the pattern like that, it's called arithmetic. So sure enough, I would get 13 and then 16 as my last values. And then you're just going to add them all together, right? So we're going to take these values, we're going to add them up. Everybody's like quietly adding this. 51 is correct. Good job, Noah. It's 51. Okay, is that good? What? Oh, okay.
I'm still thinking
He's
about
lying.
the football field.
Okay.
Dog pens.
The dog pens, yes, okay. Fantastic. Okay, everybody good? Okay, that's okay, right? Plugging in numbers, adding them all up. Okay, so that's all well and good if we were doing it 6 times. But what if you were doing it like 100 times? Oh man is right. Like that does not sound like a good plan, does it? So it'd be really nice if we had some shortcuts so that we don't have to do it 100 times and actually find an answer, wouldn't it? It really would. So that's what these summation formulas 1 through 4 at the bottom are going to do for us. Okay, the next 2 slides, 1 or 2 slides I'm going to show you. They're going to give us shortcuts so that we don't have to actually calculate 100 things or whatever and add them up. The catch is anytime you get a shortcut, it means that there's something else to memorize. And you know that's true, right? You're like, yay, shortcut. Oh, I have to memorize something, right? You do. Like that's just the reality. It's a give and take relationship. So let's take a look at what we get to memorize. Okay, so these are our 4. Okay, so let me just pause for those of you who are writing things. Jot down the beginning parts of this first. Yep, just go ahead and write down. You'll be able to fit all of them on one line. So just give one line for each of them in your notes. The conditions at the beginning are just like the conditions we always have, right? C is a constant, N's an integer, positive integer. And you'll notice similar notations to what we've already seen with the I's and so forth in there. Okay. Now, the first one, anyway, we can develop just by your basic knowledge of mathematics. I know you guys can. So all this is saying, don't write this down. Let me just write it. Well, you can write it down if you want to, but all this is saying is that every time I plug a number in, I get the same C value out. So when I equals 1, I get C. When I equals 2, I get C. When I equals 3, I get C. And I get a whole bunch of C's. How many of them? N of them, because it starts at 1 and it goes to N. Yeah. There's actually, we do infinite summations in Calc 3, just so you know. So it is a thing. It's just not a thing right now. Yeah, so there's N of them as the way it's written right here. So what's a shortcut way of writing C plus C plus C plus C N times?
C to the n's power.
Close. What did you have? What did you think, Nick?
I'm with her.
You were with him?
Her.
Are you going to reference to the Twitter thing?
Okay. So, hey, Reed, if they were multiplied, it would be C to the N. But they're added. N times C, so it's multiplication. Yeah. So this is actually N times C or C times N. Okay? So however many of them you have, however many terms you have, you simply multiply that constant number times the N. Okay? This has actually got a name. It's in your notes for those of you who have them. This is called the sum of constants. All right, so if you guys were in one of my math classes that I teach for those who are going to teach elementary school, you would encounter the second one here. This one right here is actually a process that was developed by a gentleman named Gauss. And what it is doing is it's adding together here, essentially, the numbers 1 plus 2 plus 3, like this. Are you with me? Because it's I, and the I number is changing every single time, from 1 to 2 to 3. So you're just adding up a whole bunch of numbers until you get to n. So Gauss had a teacher. Gauss was 6 years old. He is a mathematician, obviously very bright, even at 6 years old. And he had a teacher who was trying to give the class something to take a lot of time. I'm sure you've never had a teacher do that, right? Give you a little bit of busy work. This was her idea. So she wanted her class to add up the numbers from 1 to 100. That's what she wanted them to do. And she anticipated that it would take them quite a while. And Gauss was able to answer her almost immediately. And the process he developed, which I won't go into detail, what he actually found out is that if you take the number at the end, right, n, and you multiply it by one number more, he didn't come up with the formula as a 6-year-old, but this is the formula that comes about as from what he did, and divide by 2, you will actually have the sum. Okay? Again, he didn't create the formula, but this is the formula that comes out of his work. So it's pretty easy to do, right? I mean, you just take whatever that number at the end. It has to start at 1 for this to work. Again, I'll show you what happens when the numbers don't start at 1. All these summations start at 1, okay? So as long as it starts at 1 and it goes to 50 or 1 and 1,000, right? You take the number at the end, let's say 1,000. You take 1,000 times 1,001 and divide by 2 and you're done. Yay for not adding something together 1,000 times, right? For real, yeah. So this actually is the sum of the first n positive integers, or you could say the first n natural numbers. That's what that is. The next two formulas come about in a very similar fashion. I'm not going to try and justify all the details for those. They are in your book. And so these do the same thing, right? So this is the numbers 1 squared plus 2 squared plus 3 squared plus 4 squared, right? It's the sum of squares is what it really is. And the way that you get that one is that you take that same n, I'm going to use that red since I was using it before, and you multiply by the n plus 1, so like it's the same thing so far, but you also multiply by 2n plus 1, and everything gets divided by 6. Okay, that's what ends up the result of doing this, adding together. And again, this is the sum of the first n positive integers squared. Or the sum of the squares of the first n positive integers, put the square in there somewhere. You're squaring them all and adding together. And the third one is cubing them all, right? You're cubing them and adding them together. And when you do that, the shortcut is actually n squared times n plus 1 squared divided by 4. And a similar description is this is the sum of the first n positive integers cubed. Okay, so just for fun, we'll end on this today. We won't get beyond page 1. Let's go back up to problem number 1 and see how the rules work. Okay, I realize it's overkill. Problem number 1 only had 6 terms. I get that. But I would like to show you that it actually works and how it works before we continue on into the next page, which we will do on Wednesday. So if you take a look at this problem here, first of all, what you see is that n is equal to 6, right? That's important because all those formulas had n in them. The other thing that you see is you see 2 pieces of summations. One summation that has times I and the other summation that doesn't. So there's actually a process, and we'll look at the rules to do this next time. that says I can break them apart. This can be 3i from 1 to 6. And was it subtraction? Yeah. And this piece can be I from 1 to 6 of the number 2. Like I can break them apart like this. Okay? So any addition and subtraction, just like with limits, just like with derivatives, I just break addition and subtraction apart and deal with them independently. So this piece right here, whoa, that's the one I wanted, is the summation rule for, it's the second one, right? It's the second summation rule. So it says, because it looks like I, oh, and there's one more thing at the beginning. Sorry, let me do that too. I can pull the 3 out in front. Again, I'll talk about that piece in a minute. Not in a minute, but in 2 days. That's not a minute at all. Okay, so the summation from I. So the 3 at the beginning, I can ignore it. It's a constant multiplier rule, just like with derivatives. This says I should be able to do 6 times 7 divided by 2. Doesn't it? N is 6. Like that top number is 6. Right? Rule number 2, top number is 6. So 6 times 7 divided by 2. And the piece over here says that I should be able to take 2 times n, and n is 6. So what is 6 times 7? 42 divided by 2 would be 21. So now I have 3 times 21 minus 12. 3 times 21 would be 63. What is 63 minus 12? 51. Oh, good, because this was not in my notes. I was really hoping it was going to work out. I was pretty sure, but it's always good to see it happen. Okay, so what we're going to do next time is we're going to continue with these properties, these rules, and show that they are going to continue to work for us. So I will change WebAssign. It will be adjusted to be due on Friday. We will finish this lesson and start 4.3 on Wednesday, and then on Friday we'll have the quiz. So that means you don't have any homework to be doing for me right now, which means if you haven't already completed the WebAssign extra credit for Chapter 3, tonight and Tuesday night would be great opportunities to get some of that more under your belt for that extra credit. Okay?
What was the Friday?
We have a quiz over 4.1 and 4.2,
Okay.
but we're not finished with 4.2 yet.
I thought you meant like the.
No, Gateways on Monday. No, just a 4.1, 4.2 quiz on Friday.